Cool. You should be recording now. All right. Hi. So today we're going to be talking more about mixing time. We started sort of building the ideas during the last lecture, but I just want to provide some intuitive foundation before we start. So yeah, suppose, we have this Markov chain and we're taking a walk. So we start at some state and each step you move to the next state according to some certain probabilities. And over time, what's going to happen is your location will become less predictable. So you're going to forget where you started eventually, right? And that forgetting part is called mixing. So eventually, the probability of being at each state settles to some distribution called the stationary distribution, which is we're going to denote as lowercase pi. So the question we're going to be studying today is, how quickly does a Markov chain converge to its stationary distribution pi? And we're going to use the concept of mixing time to help quantify this. So yeah, if a chain starts in state X, after t steps, the probability of being as state Y is going to be this quantity here, so pt of x comma y, and then pt of x and dot represents the whole probability distribution. You can think of this as a row in the transition matrix. And we want to measure how far pt of x comma dot is from our stationary distribution pi, and that will tell us how far from equilibrium we still are at time t. So that's what we're going to use to define total variation distance. So basically, if U and V are two probability distributions on the same set, then we have this distance metric. So dTV of U comma V is going to be half of, the absolute value of difference between U of Y and V of Y. Essentially, the notion behind this is, we want DTV to range from 0 to 1, where 0 means the distributions are completely identical, and 1 means they're completely disjoint. Um, and so, for example, if you have like 1, 0 and 0, 1 as your distribution, then we look at the distance as the absolute value differences, add them up. So that would be 2, but we want it to range from 0 to 1. So we take like 1/2 of that. And so that's where the 1/2 is coming from. So in our case, we also want to define like a Markov chain specific definition, right, to look at times. And so we define dTV of t to be the max worst case distance to equilibrium. So this is like looking at the distances between your stationary and pt of x comma dot, and then you're taking the max across your different starting points. So like how far can the chain be from stationary after t steps? And so what we're going to do in this process is also bring in operators and matrices. We'll see when we start proving our lemma during this talk that these will be super useful. So far, right, we've been talking about probability distributions, but the transition matrix PT can also be thought of as a linear operator or something that acts on functions. So let's unpack this a little bit. Let's say that f is some function on your states. So, it could represent reward or like any number assigned to state y. And um, after one step, your expected value of f becomes this quantity. So this is, the average value. We're trying to get the average value of f after one random step from x. And so this is, as we've probably been used to, a probability. And then this is our value of f of y. Um, and so this is just giving you an expectation of f after a step. And so P acts on f by mixing together the values of f according to these transition probabilities, just like an expectation. And so that's why we're going to call P a linear operator on functions. Another concept we want to introduce is capital pi. Um, so capital pi is going to be another operator, um, and it's defined like this. So capital pi of x comma y equals pi of y. And all that means is, capital pi is this matrix, and each row within the matrix um, is pi, or stationary distribution. Um, and so what happens when pi acts on F? That's defined by this equation right here. And what we're basically doing is looking at the stationary distribution times F of y. Um, and as you can see, this doesn't depend on your starting place X, but it gives you your pi average of F, which is the expected value of F under your stationary distribution. And it's important to note that pi f, which is this thing right here, pi f is a constant function. So it's a perfectly mixed version of f. And that's why we also call pi a projection onto equilibrium. So you're erasing dependence on the starting point and replacing it with the stationary average. The stationary, yeah, the stationary average. Hopefully that gives us some good foundation before we introduce our lemma. I can't really stop for questions, so we're just going to keep going. Um, so yeah, so now we're going to introduce lemma 1.1. So in the textbook, they say like this is about relating probabilistic distance over operator norms. And there's two parts to this lemma. The textbook introduces them all together, but I'm just going to separate it out a little bit more. So the first part of lemma 1.1 says that 2 times dTV of t. So remember, that is this quantity here. We're looking at the worst case distance to equilibrium. So 2 times that quantity is equal to the norm of pt minus pi. And let's just try to break that down. So this, like inside right, is the total deviation per row. And so PT minus pi is looking at how far the chain's transition operator is from equilibrium. So hopefully it's intuitive that it acts like a difference operator. So if you apply it to any function, it tells you how much being not mixed still affects your result. And then the norm is going to tell you how much can this operator stretch a bounded function. So if we are a little more detailed about that, um, you have this and you're basically summing across each of your rows and looking for the largest total deviation. In this case, we're looking at the matrix PT minus capital pi. Um, and then, yeah, just like before, that should be exactly twice the total variation distribution distance between PT of X, comma dot and lowercase pi. And so what we're going to show here is pretty much exactly what we just talked through. So basically we have this left-hand side and we kind of expand it out. And we can use our previous definition of dTV of t to make a substitution. So this is like looking at the difference between this is looking at the total variation distance. And then we said we can substitute it in. So that's from our previous definition. And then that just gives us 2 times dTV of t. And that's kind of the first part of the lemma. And the way to kind of think about this or interpret it maybe is like the probabilistic measure of distance from equilibrium, so how different the distributions are, is the same as what the textbook calls the operator theoretic measure of how far the transition matrix is from the equilibrium operator. So one thing is measuring how different the rows are from pi. And then the other one is looking at how much does this operator move a bounded function away from its equilibrium mean. And then those two things are numerically identical. Okay, hopefully that first part makes some sense. Um, I'm going to pause to kind of let that sink in for a second before we move on. Cool. So now we understand what it means for a chain to mix. Um, and so let's say we were in a place of almost mixing, which means that, PT is close to capital pi. So each row of PT, the distribution after t steps, is close to lowercase pi, the stationary distribution. But what happens if we want to run the chain for longer, right? Because we're almost mixed. So if we run for t steps and then for s more steps, um, we write that as this. So like p of pt sub s. Oh my God. P sub t plus s equals pt times ps. Um, and we also want to introduce like one important idea, which is once we're close to the equilibrium, applying the chain again doesn't move away. So it just keeps us there. And so mathematically, that's just expressed as pi times pt equals pi. And for now, I'm going to just take that as definition. But as an exercise, if you want to prove that this is true, that might be helpful. Cool. So great. Okay. Okay, so I'm just going to provide a little more intuition. So let's imagine our chain is already perfectly mixed because this was a concept that I was like, what does that mean? So imagine your chain is already perfectly mixed and every row of your matrix looks like lowercase pi. So if you apply the transition matrix P again, what happens? Well, you're just taking the weighted average of identical rows and you get the exact same thing back. And there's no changes. So that's exactly what capital pi times pt equals pi means. Cool. So if you want to see it symbolically again, just do the proof. It's just a couple of steps. All right, so yeah, let's go back to the idea of thinking of things that are not yet perfectly mixed. So our difference from equilibrium is pt minus pi. And so if we run for s more steps, we can just append a plus s on here and then write it like this. So this is following as a product of those two quantities. This is following from our initial definition up here. Um, and we can use this quantity here, that equality, because things will cancel out over here. Um, and so linear algebra tells us that the norm of AB is less than or equal to the norm of A times the norm of B. And that's just saying that doing two transformations in sequence cannot stretch things more than just doing each one separately. And so if we translate that back to our situation, it means that running the chain longer can't make it less mixed, right? The worst case distance to equilibrium after t plus s steps is at most the product of the distances after t steps and then after s steps. So if we look at our situation, right, in formula, that would look something like this thing right here. So the norm of p sub t plus s minus capital pi um, is at most the two norms multiplied together. And then using the first part of lemma 1.1 that we proved earlier, you can say that this norm equals 2 times dTv of t. And so we can now make some substitutions and write it like this. So again, we're just multiplying our t part times our s part. And this is something that we'll call submultiplicativity. And when something is multiplicative, um, logs can make it additive. And they just make it nicer to look at. So if we define f of t like this, using that log on your distance, then you translate this quantity on the left to this thing on the right, which basically says f of t plus s is less than or equal to f of t plus f of s. And so f is subadditive, which means that the total log distance after, in this case, two time intervals is never more than the sum of its parts. And so subadditivity tells us that the average rate of decay eventually stabilizes. So we can go down, but it can never go up. It flattens over time. And this is exactly what Fekette's lemma formalizes, right? So this is the last thing we're going to introduce today, but it just says for any subadditive function, the ratio f of t over t, which is the average rate of growth or decay, converges to the smallest possible value, the infimum. Remember, the infimum is just like the greatest lower bound, so the lowest value that f of t over t ever approaches. Um, and so we've kind of gone over these things as we've been talking, but just to reinforce, f of t over t is the log distance per unit time. And then Fekete says that this settles to a constant, and that constant corresponds to an exponential rate of mixing. So the change distance to equilibrium decays roughly like as with an exponential function. And then very last few points to just recap and summarize what we talked about within these 15 minutes. So PT describes how your chain moves. Capital Pi describes your perfect equilibrium, where each row of that matrix is your stationary distribution. And then the operator PT minus pi measures how much mixing is left. And its norm shrinks over time multiplicatively. And the lemma that we just introduced tells us this means exponential convergence, which is a well-mixing Markov chain. Cool. I'm going to stop sharing now.
All right. I'm going to share this. Oh, wait, 10 seconds. Okay, so far we've seen some interesting properties of the variation distance, but how does this tie into our larger goal? Well, our overall goal, we want to continue to investigate question 1.1, which asks how fast is convergence promised by theorem 1.1? So specifically in our context, we want to see how fast does our variation distance go to zero as t goes to infinity. Well, we've just looked at Fikete's lemma, which gives us a very interesting property. So because 2 times variation distance log is subadditive, we know that as it goes to negative infinity, or it goes to negative infinity as t goes to infinity. And if we take this function and divide by t, we then get that it must go to some negative lambda, where lambda is some positive real number as t goes to infinity. And we want to see why this is the case. So let's define a spectral gap. Well, we claim there exists some lambda greater than 0 called the spectral gap, such that we have the following. So we have a variation distance is equal to e to the negative lambda t plus little o of t as t goes to infinity. And this just directly follows from Fikete's lemma, because if we multiply like both sides here by t, then we have to add our little of t because we're looking at like asymptotic growth. And if we just take e to the power of that, we get roughly that, like after dividing by a factor of log of 2, which can be excused or like removed just because, again, we're looking at the asymptotic limit. And so our second one says just specifically for any t greater than or equal to 0 that we have our variation distance is greater than or equal to half times e to the negative lambda t. And this is just, again, another application of the lemma, but just specifically for all t rather than just looking asymptotically. So we have to keep that factor of half because we're just looking at for all t. Yeah, so this is, again, just directly implied by the lemma we just saw. Okay, let's move on to the spectral interpretation of this. We find that the spectral gap is, in fact, exactly the distance between the real components of the largest eigenvalues of T. And recall that T is just the transition matrix. And the kind of intuition is behind this is that we know that T has an eigenvalue of 1. So the distance between the real components of the largest eigenvalues of t are 1 minus the second largest eigenvalue of t. And the 1 represents the stationary value, so it'll go to the stationary distribution. And the other eigenvalue, the other largest eigenvalue, represents the non-stationary component and how fast it'll die out. So if we keep applying t, it'll represent how fast it'll die out. And if we have larger, and if this eigenvalue of t is large, then it'll take longer to die out. And if it's small, then it'll die out faster. And this makes sense because then, okay, we have small eigenvalues of t. The distance between 1 and this eigenvalue will be great. And we know the spectral gap, like if spectral gap is larger, then our variation distance will decay a lot faster, as explained here. Because by our definition here, we kind of understand that our exponential decay rate is approximately just the spectral gap. And not only this, it's bounded by the spectral gap for every t. So we know eventually we will decay by exponential rate lambda, and for every t, the decay rate is smaller than lambda until, for large t, we'll get there. So that's kind of the intuition behind this, but now let's see an actual kind of proof. So we're going to take this formula as given. We have by Gelfand's formula that for any linear operator A on a finite dimensional space and any norm on the space of such operators, we have that 1 over t times log of a norm of e to the ta as t goes to infinity is approximately max over L theta in the spec of A of the real component. And okay, the right side looks a little complicated, but the right side is just saying the maximum real component of the largest eigenvalue. And the left side looks kind of familiar, so we can kind of see how we're going to get a proof of this, but I'll just give a couple seconds to read this formula. Okay, so we can kind of see why this e to the ta is a little familiar. Remember that pt is e to the tl, and L is just t minus identity. So we notice that this just means that the eigenvalues of L are the eigenvalues of t minus 1. And so we can kind of see, we can just substitute A with L, and we can then get that this is just pt. So let's restrict L to the 0 mean space, and we'll see why we're restricting the space later. But for now, we'll just do the substitution. So you see here, we've substituted e to the ta with pt. And the reason we have t here instead of L is because we're using the fact that eigenvalues of L are just eigenvalues of t minus 1. So we used to have like eigenvalues of L, and then we're replacing it with eigenvalues of t minus 1. So this part here. So now we kind of see in the next part why we're restricting to the 0 mean space. So we are replacing pt with pt minus pi. And the only thing that changes on the right side is that we're restricting to eigenvalues outside of 1. And the reason we can do this is specifically because we have restricted to the 0 mean space, because the pi does not decay as t goes to infinity. It stays the same. It's a constant. So when we restrict to 0 mean space, we're only looking at the decay of the components that will go to 0. So the right side doesn't change, except we're restricting to eigenvalues outside of 1, because if theta equals 1, then we have the stationary component, so no decay. So then we see that we've also changed the generic norm to this specific norm, infinity to infinity. And the reason we're doing this is because, well, Gelfand's formula said it was true for any norm, and we're doing specifically a norm from infinity to infinity because that allows us to make this equivalence right here. And this equivalence, by what we've seen previously, we know that as t goes infinity, this will go to exactly negative lambda. And if that goes to negative lambda, then by some rearranging, we just get lambda equals the 1 minus the max eigenvalue of the real component of the max eigenvalue of t. And that's exactly what we stated, that the spectral gap is just the distance between the two largest eigenvalues of t. Okay, so that's kind of the proof and the intuition behind that part. So now let's see how this applies to actually looking at how fast the variation distance will go to zero. So let's define the relaxation time as 1 over lambda. And at first, you might think that this is just our, exponential rate of decay. Like, this is how fast we're going to go to zero. But this is not actually true. We only know this is true for large t. So we only know this is true asymptotically. This tells us nothing about what happens for small t. Like, for all we know, for small t, it could be a very small rate of decay. And then, eventually, after a really long time, we hit this eventual rate of decay. So it tells us nothing about like the actual time until our variation distance is small. So how do we actually look at this time? Well, that's where mixing time comes in. So we're going to define mixing time as follows. We have that the mixing time with precision epsilon between 0 and 1 is defined as just the minimum t such that our variation distance will go below epsilon. So if we just draw this on a graph, we see our red line is our variation distance and our x-axis is just t. We want to know, okay, when is our variation distance going to epsilon? And that's exactly at this point right here. So from then on, we'll have variation distance less than epsilon. So this kind of helps us actually understand a lot more how fast our variation distance goes to zero, because we can, use smaller and smaller epsilon to figure out how fast we'll decay. So we're going to consider a default choice of 1 over 2 times e. So we're going to write that our t mix is just t mix of 1 over 2e. And we can make an observation here. We note that for all epsilon between 0 and 1 over 2e, that the ratio of mixing time of epsilon to the mixing time, or the default mixing time, so 1 over 2e, it's less than equal to the ceiling of the log of 1 over epsilon. And so we see that this will actually help us a lot in investigating our overall question, because we can plug in some epsilon and we'll see, okay, like what's the ratio of the times it'll take to get to 1 over 2e versus how long it'll take to get to epsilon. It's actually like a quantifiable time. So let's see how we can prove this. Well, we've proved our submultiplicativity of 2 times variation distance. So using that, we can say this. So we have, if we plug in, mixing time of 1 over 2e for both of our, additive values, we have variation distance of 2 times the default mixing time is less than equal to 2 times the default or variation distance of the default mixing time squared. And we can then look at this generally. So if we generalize it for some k, we can just apply submultiplicativity k times, and we get the following. So it's the same thing, except we have a factor of 2 to the k minus 1, and then on the right side, it's to the power of k rather than 2. Okay, let's see how this helps us. Well, note that on the right side, so this is kind of like redundant. We know by like definition of mixing time, this is just the minimum time such that the variation distance like goes less than 1 over 2e. So we can just generalize this, and this is just 1 over 2e, or essentially less than 1 over 2e, but then we can, add another thing here, and so the inequality still holds. So if we simplify that, we get this is 1 over 2e, and then it's that to the k times 2 to the k minus 1. And if we simplify that, we just get this value right here. And the left side, we're going to leave unsimplified. But now we're going to look at minimum k. such that the left side is less than or equal to epsilon. And the reason we want to look at this, because that will tell us that this inner component is just then epsilon, or not epsilon, sorry, t mixing time of epsilon. Because we know by definition, the mixing time of epsilon is just the minimum distance such that our variation distance is less than epsilon. Minimum time such that variation distance is less than epsilon. Okay, so if we want minimum k such that that is true, then we can just say this part is less than or equal to epsilon, and that'll give us that by default. So we do some rearranging here, and we get our minimum k is approximately ceiling of log of 1 over epsilon. And why does this give us what we want? Well, remember, we said that if we have this right here, that'll tell us that this value is t mixing time of epsilon. And if you want this to be, or if you divide by t mixing time of 1 over 2e, you get k is just a fraction mixing time of epsilon over mixing time of 1 over 2e, which is exactly the ratio we wanted. So then this ratio is approximately ceiling of log of 1 over epsilon. So this has actually provided us with quite a nice ratio, again, of how to measure like how much time it'll take to get to 1 over 2e versus how long it'll take to get to any epsilon. If we look at mixing time versus relaxation time, we know from our spectral gap definition, we have this following inequality, and then we can just do some substitution and rearranging, and we'll get that the mixing time of epsilon is greater than or equal to the relaxation time. And we have here that the mixing time is greater than or equal to this, and then relaxation time is this. And we know it's greater because this log must be greater than or equal to 1 by the bounds we established on epsilon. And this kind of makes sense because relaxation time is essentially like how long until we hit variation distance 1 over e proportionally. And then mixing time is how long until we hit, epsilon. And epsilon by our bounds was less than that. So clearly that should take more time. And then I'm just going to quickly introduce a definition for the next talk. So we're going to look at models rather than fixed transition matrix T. And a model is a sequence of irreducible transition matrices Tn defined on a corresponding sequence of state spaces Xn, such that the absolute value of Xn will go to infinity as n goes to infinity. And the goal with this will be to just determine asymptotic behavior of the mixing time, or the sequence of mixing time. Yeah, so far we've just essentially established how to see how fast our variation distance will decay to 0 as c goes to infinity. Cool.
Cool. Okay, I'm gonna end the recording.
Okay, okay.